So I've been working on some extragalactic simulations that Dave provided, looking to do source extraction and identification. So I was told this was a bit of a mixed audience, but it seems like maybe everyone knows a lot more about OST than me. So I'll probably skip some of the beginning slides. But essentially, I was briefly talk about data cubes and the OSS simulation, and then move on to source detection and spectral extraction using my algorithms and existing methods that are out in the community, and also sort of throw in some initial results and then some ideas for next steps that I've had. Okay, so data cubes, they're these sort of giant 3D images, essentially. You have RA and DEC on the X and Y axis, and then along the Z axis, you have wavelength information. So you essentially have these sort of thousands of layers of images. While this provides sort of a great data to work with, there are a lot of issues with this as file sizes, finding the optimal ways to extract useful information from this data. And in regards to OST, these have been taken with the Origins survey spectrometer. So we're going to have 2,300 spectral layers covering the wavelength range from 23 to 600 micrometers. But again, you probably all know a lot more about this than me. So the simulation that Dave provided, the original size is 2048 pixels squared. After this has been confused with the OST telescope beam, this reduces to 1024 square pixels. This is roughly 5 arc-minute squares, which I guess matches the expected size of the field of view. Again, 25 to 600 micron wavelength range with 2,300, just over 2,300 spectral layers. So the simulations include Cirrus and zodiacal foreground components, as well as model galaxies. So the galaxies are sampled in regards to their inclination and position angles using Monte Carlo sampling. And the galaxy counts are a function of redshift, wavelength, and flux based on Herschel observations, calibrated to fit Herschel observations. So we have two types of objects. We have the star-forming galaxies, which are disks with a King model, and then AGN, which are single pixel sources with the wavelength and luminosity ranges shown here. So these are some images from some of the sky simulations. So on the left, we have the original image at 25 microns. On the right, this is a similar image. I'd just like to say here that it's not actually the same simulation, but on the right, this is after the convolution with the OSS or the OST beam. And then again, we have 100 microns, 200 microns, 300, 4, 5, and 6. And then, so by the time you get to 600 microns, you can see that we're kind of dealing with just this blur of light, which can make it really difficult to isolate objects from one another. And it's kind of one of the main issues I've come up against during the work that I've been doing. So I'm going to talk about source extraction, source detection, a few of the methods. I'd just like to sort of preface this bit of the talk here that I'm an optical astronomer. So if there's anything that I say that's sort of a bit naive in regards to far infrared, that's why. But most of these methods are based on sort of optical methods and other methods that have been developed for large data cubes. So from telescopes like Muse and Manga and stuff like that. So there's currently really three sort of established methods. So you can use, well, I guess four. So there's photometric pre-selection, so you can take deep or just ancillary imaging data. You can then take those catalogs and move them over to the data cube and use that as a basis for your spectral extractions. Alternatively, you can use standard source detection algorithms, such as source extractor. You can use these on pseudo narrow or broadband images created directly from the cube. So you can flatten the data cube down in the wavelength range, and you could take either the whole data cube, which we call white light images. You can take pseudo narrowband images, or you can take broadbands using a certain wavelength range, and then you can run source extractor on these images to try and detect objects. However, there's also methods where you can actually utilize the whole wavelength range of data instead of sort of squashing it all down and losing a lot of this data. Two of the main methods are this line source detection and cataloging tool, or LSDCAT, which uses a match filter approach, or MuseLit. Obviously, by the title, this is designed for Muse data, but it can be applied to other data sets. But this uses a source extractor-based method to detect emission line objects. But these are both emission line detection algorithms. So I'm just going to talk about how well these fare with the sky simulation. So firstly, I ran this on a white light image. So this is essentially the sum of all wavelength ranges throughout the cube to create this sort of 2D photometric image. It then runs source extractor, and so this is on a sub sample of the cube. This is just 100 by 100 square. And I find only 11 out of the 77 original input objects here. This isn't overly surprising. So a lot of this issue is probably at the longer wavelengths where the PSF sort of dominates and blurs all these objects into one. So I tried to adjust this and just take the first 1500 wavelength slices. So this is 25 to 100 microns. And 100 microns is where I saw that the PSF really started to become an effect. This doesn't really help a lot. I guess maybe these could be improved. I'm not a source extractor expert, but it seems like maybe we could probably find a few more of these objects with a bit of tweaking of the parameters. But again, it didn't really help a lot. Instead, I took just the first 100 wavelength slices. This seemed to help a little bit, so we recovered 23% completeness instead of the lower range that we had before, with about 14. But again, it's not really ideal. We're losing a lot of the galaxies and the sources and the AGN that are included in the cube. So I started looking at LSDCAT. So the way this works is it's essentially this 3D matched filter approach. In essence, this is a 3D convolution of an emission line template across the cube. It's a Python-based software package, and the way it works is you apply a medium filter, and this removes the continuum from each of the objects and just leaves you with the emission lines. You then apply a degree of spatial and spectral filtering across the data cube, and then the software does this cross-correlation and tries to identify emission line sources directly from within the data cube. So as for results, we do find an improvement over the standard source extractor methods. So we get about 30% completeness here. This has been quite generous on matching the objects. So I should have said previously, but you can see the green crosses here are the original input objects, and the red circles are the detections for each of the methods that I'm showing. So the way LSD-CAT works is it identifies the emission line sources and where they're located centrally. So they're not always centrally located within the sort of the flux area of the galaxy or the AGN. So being a bit liberal with what we say is a match. So we're saying these are very obviously matches here, but this one here is likely to be associated with this galaxy here because it gives you a different identification from this one here. So we get about 30%. And then finally, we have, I just realized I didn't change the title here, but this should be Muselet. And again, Muselet is designed to be work on Muse data. Again, optical data, so we're not really dealing with the varying PSF here. But essentially what this does is it creates these white light image along with color and narrowband images. So I think it creates 3 color images across the data cube. So in optical, it would be RGB, not RGB, sorry. It essentially just splits the data cube up into 3 separate bands and creates these 3 broadband images. And then what it does is it creates narrowband images. So this is 5 wavelength slices of the cube. It runs source extractor on each of the narrowband images. And then it estimates the continuum from either side. And then it combines all these catalogs together to find objects and then uses a line list to estimate the source redshifts and associate line detections with a single source. So some of the issues we face here are, so I think what this is that the way it combines the lines together, it requires a spatial sort of resolution. So you give it a minimum spatial distance where an object should be associated with each other. And what we find is there appears to be this sort of like grid of detections. This is much worse when I ran it the first time. You essentially just got sort of like a complete grid of all the detections, and it looked awful. So these results are just using the first 1500 wavelength slices. This is before the PSF really starts to blur all the objects. However, still we only get about 20%. And again, this has been liberal with the with identifying objects with one another with the input. So in summary, for the source detection, I think maybe each of these methods does have some prospects, but overall it's not really finding a good sample of the sources. I think the future of doing this and the way forward is to maybe take certain parts of these methods and combine them. So for example, the LSD-CAT method, the medium filtering does really well to remove the continuum. And this will let you identify emission line objects really, really well. But I think the way that LSD-CAT finds the objects is maybe a bit flawed when looking at this data. And it doesn't really optimally find all the objects. So maybe sort of a combination of this medium filtering with maybe some of the elements from Muselet and create some sort of custom algorithm might be the way forward. Alternatively, I had thoughts that maybe an iterative approach might be good. So find some of the brightest objects, maybe model them and subtract them from the data, and then rerun source detections again, and try and find some of the smaller objects. So once we've detected the sources, then you want to extract the spectra. This is kind of why I was invited to work on this data, because of a paper I put out and some software that I designed. Again, I'm an optical astronomer, so this was designed to work with Muse data. I didn't ever really think about wavelength varying PSFs. So this has been sort of the main issue. Again here. I'm just going to briefly talk about what sort of standard methods are for extracting spectra from data cubes are. So So we have aperture extractions and then segmentation extractions. So you have a field and you identify all the objects, and then you can either place apertures over each of the sources and extract all the spectra from with it, all the spectra from each of the pixels within the aperture, weight it by maybe some broadband photometry or the white light image created from the data cube. Or we have segmentation extraction. So this is where you run source extractor or something similar, produce a segmentation map, which sort of highlights the object's morphology. And then you, again, extract all the spectra from the pixels within this, weighting it some way. The issues with this, so the aperture extractions, so it might not be so much of an issue for the OSS data because the PSF's mostly going to blur a lot of the objects into sort of circular. But here you can see that we've got extended sources, maybe slightly edge on objects, and your aperture is not really going to sample all of the data necessary, and you're going to miss a lot of useful information out of there. The segmentation extraction is a little bit better, but then you've still got to base it on photometry. If you don't have ancillary data, then you've got to do it from the data cube, and the photometry you get from that isn't very good, so that the images you produce from data cubes aren't really ideal. So I thought there's got to be a better way. You've got these huge 3D data cubes with a wealth of information. There must be a good way to sort of weight the extractions and really make use of all this data. So I came up with this software we called AutoSpec. The GitHub repository is here if you want to have a look more, or there's the paper. And essentially what this does is it combines these established extraction methods, so aperture or segmentation, and it extracts a preliminary spectrum using these methods, and then it uses this spectrum as a reference and then goes back to the data cube, and it cross-correlates this spectrum with every spectrum within a sort of a subcube around the object.
Hi, Alex. Sorry, we're over time already. So if you want to, yeah, just hurry up a little bit.
Yeah, no problem. I'm getting close to the end anyway. And essentially, this is shown to deblend sources, and it increases signal to noise. So I'll skip this. This is just examples. Here are some examples from the OST simulation. So these images, this is the white light image created from the data cube. These are centered on the object. So this is one here, and then this is centered on this object. And these are the weight maps that are created. So you can see here it doesn't do so well for the fainter sources that are located behind other objects, or that sort of interfered by these brighter objects. But when you've got the brighter objects, it does well to remove any contaminants. And this is just the retrieved spectra. You can see that they're missed some of the lines. So the yellow, these are the two spectra here. You can find that some of the lines are coming through on both objects, which again is because of this they're not completely deblended from each other. Again, just another example, and here's a final example. And then we can compare this to the input. So we find that it does reproduce the input fairly well, but it does miss some objects. And here again, a lot of this continuum is influenced by the brighter source here. So you can see that the original input here in blue follows similar continuum to the orange here. And again, to improve on this, I think we need some sort of more iterative methods where we identify the brighter sources, model them, subtract them out, and then go back and extract again. Okay, and that's it. Sorry for going over time.